In this video, we're going to take another look at the chain rule. In particular, we're going to combine the chain rule with the general power rule. So let's recall what the general power rule stated. We had y equals x to the nth power, where n was any real number. Let's remind ourselves that n was equal to any real number. Then we said that the derivative y prime was equal to n, which was the exponent. We bring down the exponent, times x to the n minus 1. So if we had, say, x cubed, the derivative was 3x to the second power. Now we're going to expand this idea a little further. Instead of raising x to the nth power, we're going to raise a function, f of x, to the nth power and consider its derivative. And in this case, we're going to need the chain rule because we're considering a function raised to a power. And this is the composition of two functions. We have an inner function f. The outer function is raising to the nth power. So the derivative in this case will be y prime is equal to the power times f of x to the n minus 1. And now we need to consider this additional piece times the derivative of the inner function, which is f prime of x. So we have y prime. If we start off with y equals f of x to the nth power, then y prime is n times f of x to the n minus 1 times the derivative of this inner function, whatever this inner function is. So let's take a look at an example we have already here. If we have some function, in this case now, our function is y equals x cubed plus 2, all raised to the 2000th power. So in this case, we have our inner function is f of x. F of x is equal to x to the third power plus 2. And we're raising that to the 2000th power. So n is 2000. So in this formula over here, we have f of x is equal to x cubed plus 2, and n is equal to 2000. We're going to need the derivative. So let's take the derivative of f. F prime is equal to 3x to the second power plus the derivative of 2, which is 0. We have all the information we're going to need to find y prime. So let's go with the formula. Y prime is equal to n times f of x. I'm going over here. F of x, the n minus 1 times f prime of x. So n is 2000. We have here. N is 2000. And then f of x is x cubed plus 2. X cubed plus 2 to the n minus 1, which is 2000 minus 1 plus 1999, times the derivative of f, which is 3x squared. We can combine a little bit here, if we like. We can multiply this a little. 2000 times 3 is 6000. And I'll bring the x squared out in front. Times x cubed plus 2 to the 1999. And that's about as far as we can go for y prime. Don't really need to expand that. This is a nice simplified version. So let's take a look at another example that illustrates, or at least helps verify this, if we consider a smaller value of n. Let's consider, for instance, another example. Example 2. And this will help us feel a little bit better about this new combined approach. Let's consider a smaller value for n. Let's say we have x to the 5th plus 3 to the second power. And we want to apply this power rule here. And we could say this general power rule with the chain rule. We have y prime, we consider the derivative n is 2, and then this inner function is x to the fifth plus 3 to the n minus 1, which is just 1, times the derivative of what's inside, that's 5x to the fourth plus the derivative of 3 is 0. And then we can simplify this a little further. 2 times 5 is 10, x to the fourth, and then we have x to the fifth plus 3. And now, let's just go a little further. We can actually multiply this out. It will help us when we do our verification and finding the derivative another way. It will help us to expand this a little further. So I'm just going to multiply 10x to the fourth and then distribute that through the parentheses. So 10x to the fourth times x to the fifth is 10x to the ninth, and then 10x to the fourth times 3 is 30x to the fourth. So there's our derivative using this combined approach. We could also have found the derivative by first expanding. So let's change this a little bit. Well, let's make it a little more really different here. So if we have y equals x to the fifth plus 3 squared, I can actually expand this using the FOIL approach, if you will. So we have x to the fifth times x to the fifth is x to the 10th. So what I'm doing is I'm going to write this out. I have the luxury of expanding this since the exponent is small enough. And then I'm going to differentiate to see if I get the same answer. X to the fifth times 3x to the fifth, and then another 3x to the fifth, and finally 3 times 3. Notice I'm not taking a derivative yet. I'm just multiplying out this expression. And then I'm going to differentiate. So there's y. Now let's find the derivative. If I take the derivative just using the standard power rule, that's 10x to the ninth. And then here I have 5 comes down, 5 times 6 is 30, x to the fourth, plus the derivative of 9 is 0. So here I have y prime is 10x to the ninth plus 30, these two match. That's what we want. So we saw using the general power rule combined with the chain rule is one approach. And we can do that with large values of n. We can do that here fairly easily with large values of n being 2,000, 3,000, 10,000. That's great. If we have a small value of n, we can actually multiply this out if we want and then differentiate it. But it does require some additional algebra steps. And the algebra becomes really messy, virtually impossible without a computer algebra system. So if the values of n are too high. So this is a nice rule, specifically if you have higher powers of n or if you just want to avoid the algebra. But this is a nice way to check, make sure that it makes some sense. I hope this helps you understand combining the general power rule with the chain rule.